Okay, hello students, dear students of third year secondary. This is your physics session. My name is Ahmed and I teach physics. Today we continue the general revision part 2 about integration of ideas. This is our last revision and the final ones. We intend to comprehend the ideas and we integrate them together to be able to, inshallah, perform in the best way in the coming exam. Let's continue with an example. Here, number 5. We finished 4 exercises last time, or 4 workouts. Today we continue number 5. A circular coil of radius 5 cm and number of turns 3 turns carries currents of intensity 1 ampere along a straight wire in the same plane of the coil and at a distance 10 centimeter from it, carries current as in figure. Calculate A, the value of current in the wire that makes a flux density at the center of the circular coil vanishes. B, magnetic flux density at the center of the coil when reversing the direction of the current. Now, what do we have here? We have two things. We have a wire and we have circular loop. There is a current passing in the wire as indicated in the diagram, and there is also a current passing in the circular loop in the direction shown in the diagram. Now I have currents, two currents, and I have wire and circular loop. So by drawing this, pay attention here, we have here the distance between the wire and the circular loop. From this point to that point is 10 centimeter, and the radius of the circular loop is 5 centimeter. Now he gave us the number of turns in the circular loop, 3 turns, and the radius 5 centimeter. And he said also the I sub C, which is the current passing in the coil, is 1 ampere, okay, indicated here. And the current passing in the wire, I put it I sub W, which is the I of the wire, the current passing in the wire. This current is the direction is shown in the diagram, but I don't know its value. That's what's needed. I need to calculate the value of the current passing in the wire. I have the distance 15 centimeter. 15 centimeter is the distance from the wire to the center of the circular loop. And as we know here, the radius is 5 centimeter. When we subtract 15 minus 5 equals 10. So the distance from the wire to the circular loop itself is 10 centimeter. This is useful when we apply the rule. So I extract the information, the number of turns, 3 turns. The radius of the circular loop is 5 centimeter. The current passing in the coil is 1 ampere. And the distance is 15 centimeter. The distance, pay attention, this distance is from the wire to the center of the circular loop. It is not from the wire to the beginning of the circular loop or the circumference of it. So that's why I have to subtract 15 minus 5 to give me this distance as shown in the diagram. Now, what's needed? The current intensity passing in the wire. That's what I need to calculate. And also he wants the total magnetic flux density. Of course, the total magnetic flux density will be a result of the two magnetic flux densities. One comes from the wire and the other one from the circular loop. And we have to get the total of them, the total of the magnetic flux densities. All right. Let's start now from the beginning. He said he wants the calculation of the value of the current in the wire, but he said the current in the wire that makes the flux density at the center of the circular coil vanishes. So this is the clue to answer the question. He said to make the magnetic flux density at the center of the circular coil vanishes. What does it mean vanishes? Vanishes means he needs It's at the neutral point, and the neutral point, we know that the two magnetic flux densities, they cancel out. So here you have the magnetic flux density, the B sub T, or the total magnetic flux densities equals B sub C minus B sub W. Here, B sub C is what is the magnetic flux density of the coil minus BW. What's BW? B is the magnetic flux density and W is the wire. So we subtract the two of them. All right. Why we subtract the two of them? Because simply it is a neutral point. At the neutral point, we know that the two magnetic flux densities, they are equal to each other. And because they are in the opposite direction. Now pay attention here to the direction. I put it in very bold font so that you can see it clearly. Here you have the direction of the current in the direction from right to left. And here you have the direction of the current in the circular loop. As you see here, they are opposite to each other. This goes from right to left, and this goes from left to right. Okay, so this goes like this. It's clockwise, and this one is from right to left. So the two directions of the currents, or the direction of the current passing in the wire, is exactly opposite to the direction of the current passing in the circular loop, and that's why we subtracted them. So this minus between the two magnetic flux densities, they give me 0. Where did I get 0 from? Because it is neutral point. All right, and he said that it is at the center of the circular coil vanishes. So BT must equal to 0. All right. When BT equal to 0 and we subtract BC minus BW, that makes BW equal BC. Okay. Now, all we have to do now, once we reach this conclusion that the magnetic flux density of the wire equals the magnetic flux density of the coil, all we have to do is just put the value of the magnetic flux density of the wire. And we know it is the rule that says the magnetic flux density of a wire is mu n I over the distance. Now, the distance of what? The coil, I have the number of turns of the coil, mu, magnetic permeability, IC is the current passing in the coil. I'm talking now about this part, the lower part, okay? So the left-hand side of the equation talks about the lower part of the diagram. So mu, magnetic permeability, N is the number of turns of the circular loop or the circular coil, I sub C is the current passing in the circular coil, and here divided by 2R. R is the radius of the circular loop. So this left-hand side, all this talks about the lower part of the diagram, which is the circular loop. Now, I put this in the left-hand side of the equation. Let's talk about the right-hand side of the equation. In the right-hand side, I talk about the magnetic flux density of the wire. And the rule says to calculate the magnetic flux density resulting from a wire, from a current passing in the wire, I put the rule mu I over 2 pi d. As you see here, mu over 2 pi, all this part is constant. So I only need two things. I need the current in the wire, and I need the distance. All right. So I sub W, that's what needed. So I have everything except the IW, which is the current of the wire. So I'm going just to plug the numbers. Let's now do it carefully. Now, as you see here, mu with mu, so I can cancel this with this, right-hand side and left-hand side. I cancel mu from both sides. I can also cancel out 2 from here and 2 from here, 2 in the denominator, and the other one, the other 2 is also denominator. So I cancel this 2 with this 2. I have here n over r because I cancel this part and the part I cancel them. So I have now n over r multiplied by I sub c, the current of the circular loop, equals this part. Now I cancel this and I cancel this. So I have 1 over pi d, okay, multiplied by IW. So I did this to simplify the equation before I plug in the numbers, okay, so that I don't have to put numbers and then cancel them out again. And this will make the calculation easier and also will save time. Now look here, number of terms n equal 3. I just put it, all right. The r, the radius is 5. From where did I get 5? Look at the diagram here, 5. 5 centimeter. I don't have to convert it into meter because I just put the other one in also centimeter, so I don't have to make the conversion twice. Now, if you ask me why sometimes we have to convert into meter and sometimes we leave it as it is, I leave it as it is, or we leave it as it is when they cancel out. When I have two sides of the equation, and here I have centimeter and here I have centimeter, so they cancel out. But when I make calculations, if he asks me to calculate the magnetic flux density of a wire resulting from the current in the wire, then I have to convert the centimeter into meters to get the final answer. But when I make equation and I equate two things, and here I put centimeter and the other side I put also centimeter, so I don't have to make the conversion twice. That's why I leave it as it is. So here I have 5 centimeter, right, from here, comes from here, this is the radius of the circular loop, multiplied by the current in the circular loop or the coil, which is 1 ampere, equals, here I have 1, I put pi as it is, and the distance. The distance here is the sum of here, this part and that part, right? Because here I have the wire, and here I have the point at which I would like to calculate the density at. So the density will be calculated at exactly the center of the coil, which means that the distance is all this part, 5 plus 10 equals 15 centimeter. Now, as you see here, I have everything except I sub W, or the current in the wire, all right? So pure algebra, 3 times 1 equals 3 divided by 5, and here I have 1, I replaced pi by its value, 3.14 or 22 over 7, and here I times 15. When I finish the algebra of this part, I can get I sub W, which is the current in the wire, and the current of the wire, if we make the calculations, it will be 28.29 ampere. So 28.29 ampere, this is the current passing in the wire, which will make the total magnetic flux densities equal 0. Now let's talk about the second part, which is part B. He said calculate the magnetic flux density at the center of the coil when reversing the direction of the current. Okay, now everything is the same because he did not specify any like another thing. He just said the magnetic flux density at the center of the coil when reversing the direction of the current, which means that everything is the same. Everything is the same, including distances, including radius, including the value of currents. One thing only changed, which is the direction of the current. It changed only. He said the magnetic flux density when at the center of the coil when reversing the direction of the current. Now, when I reverse the direction of reverse the direction here, what should I do is because when I reverse the direction here, look, this is from right to left. If I reverse the direction, this one, so instead of the current moving or turning like here clockwise, it will be counterclockwise. Now, when the current is moving counterclockwise or rotating counterclockwise, in this case, the two currents, the one passing in the wire and the one passing in the coil, they are in the same direction. Let me repeat this point again. When the current is reversed, that's what he wants. When the current reverses its direction in the circular loop, it means that instead of going clockwise, it will go counterclockwise. When it goes counterclockwise, it means that here you see it will go this way, and here it will go that way. So the two directions are the same. Once the direction of the current is reversed in the loop or the coil, all I have to do is to change the total magnetic flux density will be BC plus BW. Why plus? Because the two currents are in the same direction. In that case, the two currents are in the same direction, so the magnetic flux density, the total magnetic flux density resulting from the wire and resulting from the coil at the center of the circle equals BC plus BW. All right. I think we have to put again the same value, the same rule. I need what is the law to get the magnetic flux density of the coil? It's mu n I over 2r. And here I put IC just to specify that this part belongs to the coil. Now plus the magnetic flux density of the wire is mu I divided by 2 pi d. And as we know that I can cancel this 2 with this 2 and this mu and with this mu, or I can take mu as I don't cancel. Yeah, it's important. Last time we canceled because we have two sides of the equation. In this time I don't cancel because I add them. I need the value. All right, I need the value, the total value of the magnetic flux densities. I need the total value of them. So I just deal with it as it is. I don't cancel mu and mu. I just take mu as a common factor. So this mu is a common factor. And here I have n I sub c divided by 2r. Plus I took this as common factor outside. So I have 1 at the numerator. And in the denominator, I put it as it is, 2 pi d I sub w. All right. Now, I can here put the brackets, and I put the value of mu, which is the magnetic permeability value. The magnetic permeability value is 2 times pi 10 to the power of negative 7. That is the value of the magnetic permeability. I put it. And in between the brackets, let's now put the value of each item. Here you have n, the number of turns of the coil is 3, multiplied by the current passing in the coil, which is 1 ampere, divided by 2r. Here the 2r and 2r, I can the 2 from here, if I take this and this as common factor, and here it should be 4, like this 4 pi 10 to the power of negative 7, change it into 2 because I put here 2 as a common factor in the denominator and cancelled with the 4, it gives me 2. Okay. Here you have the r, which is 5 10 to the power of negative 2. This is 10 to the power of negative 2. And here the denominator is 2. 2 also we get rid of this 2 because we get this and this outside in the bracket. So here I have pi, and d is the distance between the wire from the wire till the center of the coil, which is 15 centimeter. I changed 15 centimeter into meter by multiplying 10 to the power of negative 2. So I make the conversion in this case because I need a value. Okay, so 15 times 10 to the power of negative 2 multiplied by the current of the wire, which I calculated before. Okay, I calculated the current of the wire, and we got it 28.29. So here you go, I put all the numbers, and as you see, I have everything included here, except the BT, and I can get BT. So this is one that I put it as it is. It should not be here because I put the value of IC as 1 ampere. So when I put I make all the algebra in that part, I have the total magnetic flux density equal 7.54 10 to the power of -5 Tesla. Tesla is the unit of magnetic flux density. All right. So as you see from this example, I integrated the two parts. One part is the magnetic flux density of a wire, the magnetic flux density of a coil or loop, and then we get the total of them if the currents in the same direction and if the currents are in the opposite direction as well. Okay, let's talk about another example. Let's talk about number 6. An electric current I passes through a circular coil of 3 turns. If the magnetic flux density at the center of the coil is 1.2 10 to the power of -4 Tesla, calculate the magnetic flux density at the center of the coil if the number of turns becomes 6 turns with the same intensity of current. Okay, so let's take it step by step. What do I have? I have two cases. Okay, I have two cases. Each one will result in different value of magnetic flux density, and the two cases depends on the number of turns. So let me repeat again. What do I have? I have electric current, right, passing through a circular coil. So how many coils do I have? I have one coil and 3 turns, made of 3 turns. Now, what will I change? I will change what? I will change the number of turns. So when I change the number of turns, what happens to the magnetic flux density? It changes as well. Now, because of this, he wants the ratio, he wants the magnetic flux density at the center of the coil. In what case? If the number of turns becomes 6. So the number of turns was 3 turns in the first case, or in the first state, or initially, or in the beginning. Now, when the number of turns changed from 3 turns into 6 turns, what happens? The magnetic flux density changes as well. What does he want? He wants us to calculate the magnetic flux density at the center of the coil in the second case. In the second case, it means that he wants the magnetic flux density when the number of turns becomes 6 turns. All right, that's what's needed. Let me repeat again what's needed. He needs us to calculate the magnetic flux density when the number of turns of the coil becomes 6 turns. Because in the beginning, the number of turns were 3 and then change it into 6. All right. Now, I have here the value of the magnetic flux density in the beginning, which is 1.2 10 to the power of -4 Tesla. And he wants it in the second case. Now, let's now start. What is the rule that we use to calculate the magnetic flux density at the center of the coil? B sub C. C stands for coil or circular loop. So B sub C equals mu Ni over 2R. What is this? This is the rule. Okay, this is the rule concerning the circular loop or a coil. So B sub C equals mu Ni over 2R, where N is the number of turns, I the current intensity, and R is the radius of the loop or the coil. Now, because everything is the same, the current is the same, all right? Because the current is the same, I can now make a comparison or a ratio between what? ratio between the magnetic flux density in the first case and the magnetic flux density in the second case. Let's now assign a symbol for the first case. The first case is B1. The magnetic flux density B1 when the number of turns was 3. Now let's assign B2 for the magnetic flux density in the second case when the number of turns becomes 6. So I put here B1 over B2 as a ratio between the two of them equals N1 squared over N2 squared. Where did I get this from? Look at this rule. If I put B here, B1, and I put here N1, and here I put R1, I will find that at the end, when I divide, I put this one B1 and put everything here 1, and then rewrite the whole rule again and write B2, and then divide the two equations. When you divide them, you end up with this B1 over B2 equals N1 squared over N2 squared, which is the same or equivalent to R2 squared over R1 squared. Pay attention here, why here I have N1 over N2, but in the other part I have R2 over R1. Where did it come from? It comes from because R here is denominator, and that's why it is reversed. So anyway, if you write the equation of the first case, write B1, N1, I1, R1, and write then B2 equal N2, I2, R2, and you divide the two equations and you have this result. Okay, which one of them I'm going to use? I think I'm going to use the first one because I have number of turns. All right, so I will use this one, B1 over B2 equals N1 squared over N2 squared. What's N1? He gave it to me 3 turns. What's B1? Given also to me 1.2 10 to the power of negative 4 Tesla. What's N2? The number of turns in the second case, 6 turns. And B2 is what's needed. So I need to calculate B2, the magnetic flux density in the second case. I have everything except B2. So here you go. All we have to do is plug in the numbers. So B1 over B2 equals N1 squared over N2 squared. That's the rule. Replace B1 by its value. B1 equals 1.2 10 to the power of negative 4 divided by B2. I don't have B2. That's what I need to calculate. Equals N1 squared. N1 is 3 turns squared. So 3 power 2 divided by N2, what is the number of turns in the second case? 6 turns. So I put 6 here. Squared, power 2. So here, after finishing the calculations, because I have only one thing unknown, which is B2, I will get B2 equals 4.8 10 to the power of negative 4 Tesla. And that's the final answer. So as you see here, we did not get it through a diagram, we get it through a ratio. All right. So when I have a coil and the number of turns changed, and he wants us to calculate one magnetic flux density value, I can use this rule to get what he wants. All right, question 7. A rectangular coil of area 50 centimeters squared consists of 100 turns and carrying 1.2 ampere current. Is put in a regular magnetic field of density 5 Tesla. Find the torque acting on the coil in the following cases. A, if the coil is parallel to the magnetic flux density or lines. If the coil is perpendicular on the magnetic flux lines. And C, if the coil makes an angle of 20 degrees with the magnetic flux lines. Okay, let's take it step by step. What do I have here? It is very important to understand what do I have and to have a visual idea about the question itself. So the question says, I have a coil, and he gives us the area of the coil and also the number of turns and the current passing in the coil. And what happened to this coil? He said the coil is put in a magnetic field, and he gave me the value of the magnetic field density, 5 Tesla. What does he want? Find the torque acting on the coil. We know that the torque acting on the coil, tau, can be calculated by a certain rule, and are going to use this. So, but he has here 3 cases. I assume that in exam he might, if he asks a question like this, he will specify one case only. Here I included 3 different cases, but in real situation of exam, he will ask only about one part, but I integrated the 3 different ways of the question, because the question can come as he wants if the coil is parallel only, or if the coil is perpendicular only, or makes an angle. So I put the 3 of them so that when we go through them step by step, you will understand all the 3 cases, and these are the style of questions of exams. Now look here, the first thing is I'm going to extract the information as usual and then try to join them with a rule, but this is the normal way of handling it. But I drew the diagram of the question. Sometimes drawing a diagram will give you a visual aid of what's going on. So if you look here at the case, I want you to have a visual idea about the question. He said here that I have a coil, all right? And this coil, as we know, has a magnetic dipole. And we know magnetic dipole is perpendicular always on the plane of the coil. Now, do not be confused between the magnetic dipole and the plane of the coil. The plane of the coil is this part, all right? The magnetic dipole is perpendicular on it. Now, imagine you have a paper, you put the paper on the disk, and then you put your pencil perpendicular on the paper, all right? So when you turn the paper with the pencil, they don't have the same direction. They are always perpendicular on each other. And that's why I put the coil here and the magnetic dipole as an arrow. This thick arrow is the magnetic dipole direction. And as you know, the magnetic dipole goes down and the coil plane is horizontal. So the angle between them is 90 degrees. Now, this coil is placed in a magnetic field, and the magnetic field has a magnetic flux lines, and this is the direction of magnetic flux lines. Okay, so it is from left to right. This is the magnetic flux lines from left to right. Where is the direction of the magnetic dipole? Look at the arrow, it is down. What is the angle between them? Between what? Between the magnetic flux lines indicated here in this arrow and the magnetic dipole direction. All right, what's the angle between them? Yes, it is 90 degrees. Now the angle is 90 degrees, and that's why what do you think what will happen when I have 90 degrees? Tau or the torque will be minimum or maximum, or it will be 0? It will be maximum. Why maximum? Because the angle is 90, and we know that sine 90 equal 1, and this will make it maximum. All right. In the second case, he said the magnetic or the coil is perpendicular on the magnetic flux lines. So I drew here a diagram. Look here at the magnetic flux lines. It is from left to right in that direction. And this is the coil plane. And I care so much about the magnetic dipole because when I compare directions, I compare between the direction of the magnetic dipole and the magnetic flux lines. Look here at this arrow and that arrow. Are they along or parallel? Yes, they are. So they are parallel. What is it that is parallel? The magnetic dipole and the magnetic flux lines. Pay attention. The question says the coil plane is perpendicular. Yes, the coil plane is perpendicular, but I don't consider the coil plane. I consider the magnetic dipole direction. All right. This is a very confusing part, and please pay attention. What do I look at? I don't look at the coil. If the coil is perpendicular, this automatically means that the magnetic dipole moment is perpendicular on the coil, which will make the angle between the magnetic flux lines and magnetic dipole direction 0. Why the angle is 0? The angle is 0 because they are parallel to each other. They are, I mean by they, magnetic flux lines and magnetic dipole. They are parallel. Look at this arrow and that arrow, they are parallel. All right. And this happens when the coil is perpendicular on the flux lines. And this, of course, will give tau, or the torque will be vanished. It will be momentarily 0. Now, during the rotation of the coil itself, I don't have maximum or minimum when it is rotating in the middle, but I have an angle between them. Again, what is the angle theta? The angle is between the magnetic flux lines and the magnetic dipole direction. All right? So when the coil is turning inside a magnet or placed affected by magnetic flux lines, I care about the direction of the magnetic flux lines with the magnetic dipole. So the angle between them here is theta. All right. Now, he said the coil makes an angle with the magnetic flux equals 20. Where is this 20? Is it theta? No, it's not theta. Theta is the angle between magnetic flux lines and magnetic dipole. So the angle he gave me, it is not theta. He gave me the angle which is this one. So to get theta, I need to make 90 minus the angle he gave me. Pay attention because this is very tricky, and when it comes in exam, many students just put the angle he gave me in the question. He just write sine 20. Now, sine 20 means the angle is not this one. He give me this. I have to put this. The law says theta is between the magnetic flux lines and the magnetic dipole. That's why I need to put 90 minus 20, which is theta, this one. All right. Now, after having this visual idea about the three cases, let's now do it and get the final answer. All right. So look here at the law says that the torque equals BIAN sine theta. All right. BIAN sine theta. I call it this way. Okay. So here BIAN or BIAN, I can put the numbers here. B equal 5, I equal 1.2, A equals 50 times 10 to the power of negative 4 because I converted into meter squared, and multiplied by n, which is 100. So as you see here, BIAN, I have the values of all the things required. But tau is not BIAN, it's not BIAN, it's BIAN sine theta. Okay. So tau equals BIAN sine theta, and in the first case, the angle is 90. Back again to the diagram. Where is the 90? The coil is parallel. Where is the 90? The 90 is the angle between the magnetic dipole going downward and the magnetic flux lines going from left to right. So the angle, this one, is 90 degrees. Okay, this angle between this and this is 90 degrees. So I just plug in the numbers, BIAN, and multiply it by sine 90. We know that sine 90 equals 1. So this gives me 3. So tau equals 3. And what is the unit of tau? It is Newton meter. Newton meter. That's the unit of tau, the torque. which is the maximum torque, because he asks in the question, what is the maximum torque? And the maximum torque is 3 Newton meter. So case B, or the second case, he said when the coil is perpendicular on the magnetic flux lines. Okay. When the coil is perpendicular, once again, we don't look at the coil direction, we look at the magnetic dipole direction. And we look at this magnetic dipole direction as you see here, and the magnetic flux lines. They are parallel. Look at this one and that one. They are parallel. When they are parallel, what is the angle between any two parallel lines? 0. So I put here tau equal BIAM sine theta, and theta here is 0 because the two lines are parallel to each other. Now 0 multiplied by anything equals 0. So tau here in the second case is equal to 0 Newton meter, which is nothing. So I don't have a torque in this case. Now the third case, he says, in the third one, he said if the angle, let me read the title again from the quote. He said, if the coil makes an angle 20 with the magnetic flux lines. Pay attention. He said, if the coil makes an angle, not the magnetic dipole. He said the coil itself. The coil makes an angle 20 with the magnetic flux lines, which means that this is the angle he mentioned. He mentioned this one. In the law, theta is this one. So I have to do what? I have to get this one from the total, 90. So 90 minus 20. So tau here in the third case equals BIAM sine 90 minus 20. You know now why did I subtract? I subtracted here 90 minus 20. So when I plug in the numbers and I put all the values, I get the total answer, or the final answer is torque equals 2.82 Newton meter. Okay, so 2.8 means that it is less than maximum. Okay, less than maximum. Okay, after finishing all this part, let's now talk about the electric measurements. And as you see, we have 3 electric measurements, and we can convert galvanometer into ammeter, and we can convert it also into voltmeter, and we can convert it into ohmmeter. And we have questions concerning how to convert the galvanometer into ammeter or into voltmeter or ohmmeter. But also we have some questions involving calculations. Look at this one. He said a certain galvanometer has a resistance 2 ohm where a current of 5 milliampere is required for full-scale deflection. What shunt resistance must be used to convert the galvanometer into a meter whose maximum range is 10 ampere? So what do I have here? I have galvanometer. I have galvanometer, and the galvanometer, as we know, has a resistance, a small resistance, 2 ohm, where a current of 5 milliampere is required for full-scale deflection. What does it mean, full-scale deflection? It means that this is the maximum current passing. What shunt resistance? We know that to convert galvanometer into ammeter, we have to use a very small resistance, and it's called shunt resistance. So he wants the value of this shunt resistance. And because of this, when I have shunt resistance, I can now convert the galvanometer into ammeter, as you know from previous lessons. So shunt resistance must be used to convert the galvanometer into ammeter, okay? Whose maximum range is 10 ampere. He gives me now the maximum current, 10 ampere, all right? So let's now extract the information. The first piece of information I have is RG, which is the resistance of the galvanometer, 2 ohm. Where did I get this 2 ohm? He gave it to me. He said a certain galvanometer has resistance 2 ohm. So this means that the resistance of the galvanometer, RG or R sub G, equals 2 ohm. And then he said where a current of 5 milliampere is required for full-scale deflection. So this means that the current of the galvanometer, or the current that can pass in the galvanometer, is equal to 5 10 to the power of negative 3 ampere. Why did I multiply by 10 to the power of negative 3 ampere? Because he gave it to me in milliampere. I cannot leave it as it is. I have to convert milliampere into ampere by multiplying by 10 to the power of negative 3. Fine. And then he said to convert it into to convert it into a meter whose maximum range is 10 ampere. All right. So I have two currents here. One current is the current in the galvanometer. And then when the galvanometer is converted into a meter, now it can now measure a range which is bigger, 10 ampere. So I have two values. One current of the galvanometer, we call it I sub G or IG, and the current of the ammeter, which is bigger, we put just I equals 10 ampere. And what is needed? Shunt resistance, the R sub S or RS. So we know that we have a rule that connects galvanometer to ammeter, or if we want to make the conversion from galvanometer into ammeter. The rule says RS, the resistance, the small resistance needed, or the shunt resistance, equals IG times RG divided by I minus IG. What is this? This is the rule. This is a rule which we proved earlier, and this is the rule that's used when we have galvanometer converted into ammeter. All right? So this is a rule. RS equals IG times RG divided by I minus IG. Now I have everything. I have IG. Yes, I have IG equals 5 milliampere. I convert it into ampere. So it is 5 10 to the power of negative 3 times 2. What is 2? The value of the resistance of the galvanometer, RG, 2. Over, in the denominator, I put I, which is 10, minus IG. What's IG? 5 times 10 to the power of negative 3. I put it as it is. I have everything. I just have now numbers. And when I finish the calculations, I will end up with the value of the shunt resistance, which is RS equals 0.001 ohm. All right. Now, the key to answer questions of electric instruments is to understand the symbols I'm using. So when he says a galvanometer has resistance, what is this resistance? It is RG. All right. Why RG? Because it is related to the galvanometer. A current of 5 milliampere is required for full scale. What does it mean? This is the current. Current of what? Of the galvanometer. Very simple. And then what shunt resistance? RS. And then he said convert it into galvanometer. Now, when it's converted in the galvanometer converted into ammeter, it means that I have now two currents. One current passing in the galvanometer, which is small, and then when I converted the galvanometer into ammeter, it now can measure a bigger current, and this is I. The bigger current is I, and the small current is IG. When I put the terms correctly, I can now use the rule, which is the rule that governs how galvanometer changes into ammeter. The rule says RS is IG equals IG times RG divided by I minus IG. All right, this is a rule that we use in this case. And then we have everything except RS. I plug in the numbers, all of them given to me, and don't forget to convert milliampere into ampere. And then when you finish the calculations, you get the shunt resistance. All right. So if you put everything correctly from the beginning and you understand how to extract the information, things will be much easier. And this is the last question or the last group of questions that we handle this session. By this, we come to the end of our session for today. Thank you for listening. My name is Ahmed and I teach physics. If you have any question, don't forget to drop it, or if you have any requirements to explain any part that you find confusing or you need to revise, you can select any part for revision, and we can handle it in few sessions, inshallah. My name is Ahmed and I teach physics, and see you next time. Study hard and be optimistic. Things is going to be, inshallah, easier. Thank you for listening again, and till next time.